Thank you so much. Thank you all for inviting me to be here today to speak about some of the work that I do and the um, excellent time that I had as a Fulbright New Zealand scholar. I see my program manager on the call, so thank you again very much for the opportunity. I will start by sharing my screen so that I can show you some slides that are going to tell a bit of the story of the work that I do and oh, I need to hide that note from Microsoft Teams before I get started. There we go. Share a bit about the work that I do and a bit about the sort of behind the scenes view of what it's like to be a professional astronomer. So I really like sharing this aspect of astronomy with people because it's a slightly underexplored story. This is actually what I wrote about in a book that I published a few years ago, basically telling the story of the behind the scenes life of astronomy. My book came out in 2020, which was a really interesting year to publish books. I did a lot of the sort of publicity and lead up from a Zoom screen or a Microsoft Teams screen like this. But I did get the chance to go to one wonderful book conference just before everything started shutting down. And I got to speak with other authors of popular books for the first time. And I remember sitting in a wonderful session where the topic of first lines of books came up. And everyone was going through these sort of iconic first lines of books in literature. So, Call Me Ishmael from Moby Dick, or It Was a Dark and Stormy Night from A Wrinkle in Time. And it got me thinking, well, all right, I've written this book trying to talk about what it's like to be an astronomer, to try and solve the mysteries of the universe, to go on all these incredible adventures. How do I start my book and how do I welcome people to all of these really amazing stories? And I realized the first line of my book is, have you tried turning it off and on again? So this does not sound like the start of a sweeping space adventure. This sounds like every frustrating phone call you've ever had when your internet stops working. But this was actually one of the most alarming questions that I had ever been asked while at a telescope. And I was sitting here when I got asked, have you tried turning it on and off again? And the it being referred to in this question is the telescope that you see on the screen. This is the Subaru telescope atop Mauna Kea Observatory in the state of Hawaii. And I was using it as a University of Hawaii graduate student. I was desperately trying to get data for my PhD thesis, studying incredibly far away galaxies that only Subaru could observe. And the reason only Subaru was capable of that was because it was one of the biggest telescopes in the world. It had a primary mirror that was 8.1 meters, 8.2 meters from end to end. And to give you an idea of what that means, this is what the inside of the Subaru telescope looks like. This is me standing underneath a telescope that's about the same size. So that enormous mirror is how the telescope collects light and is able to detect incredibly faint, distant, faraway galaxies. It was uniquely suited to the research that I was trying to do. So I had been working at this telescope all night. Everything had been going flawlessly. We had beautiful weather. I was pointing the telescope back and forth from galaxy to galaxy until at one point in the night, I was sitting in the control room and one of the computers in the control room made this terrible bloop noise. And I looked over at the computer and then I looked at the only other person who was sitting at the telescope on top of that mountain with me, who was the trained operator of the telescope, the expert in the room on how this immense building sized piece of scientific equipment actually operated. She looked a little concerned and she looked back at me and she said, "It's okay. I think that sound is okay. I think the mirror is still on the telescope." No, I've just shown you how big that mirror was, and the idea that it could not be on the telescope anymore, that it could have fallen off, was pretty alarming. She explained to me a little more what she meant. In this picture, the telescope is pointed straight up. So the enormous mirror that I showed you in that previous picture is sort of sitting near the bottom of the screen. Suspended high above it, you can see what looks like a little black circle. That's actually another mirror. Starlight will come pouring in from the top of this picture when the telescope dome is opened. It will bounce off the mirror near the bottom of the screen and then bounce off that mirror near the top and be redirected into a camera or a scientific instrument or whatever else we're using. The bloop sound had suggested that that mirror sitting high up in the air, the little one, was no longer being properly supported by the mechanics of the telescope. It was suggesting that a support mechanism had failed. And what that meant was that if we tipped the telescope too far to one side or too far to the other side, that mirror could come off and go plummeting dozens of feet to the floor of the telescope if we were lucky. If we were unlucky, it would hit the big mirror on the way down. So we stopped everything and tried to figure out what was going on and how to fix the problem. And we called the engineers who were specialists in working with the telescope during the day. And their immediate response was, oh, no, it's probably fine. It's probably a false alarm. You probably don't have anything to worry about at all. They said probably over and over, and it was not very reassuring. They said, you can probably fix the whole problem if you turn the telescope off and on again. And I turn my modem off and on again at home to fix our internet. I don't usually imagine doing this with a scientific instrument the size of a building, but that was the solution they had on offer. So our operator hung up and looked at me, and I then had to decide what to do. I was a graduate student, I was 24 years old, and I very badly wanted to keep observing. I wanted this to be a false alarm so that I could keep getting data that I crucially needed for my thesis. If we shut down the telescope and went down the mountain and waited for engineers to fix the telescope the next day, I couldn't just come back and start observing again. There was another scientist arriving on the mountain who had been assigned the next night of access on the telescope. I'd have to wait months or even an entire year to get back on the telescope again. On the other hand, if I went ahead and this wasn't a false alarm, I thought I would be forever known as the grad student who killed the telescope, who broke one of the biggest pieces of glass in the world. And I just had stories spinning through my head of how wrong things could go at telescopes. The one that I kept picturing was this telescope, which was in the state of West Virginia back in the 1970s. This is the Green Bank radio telescope. So it's a radio telescope, not an optical telescope, making it look a little different than the telescope in the previous picture. In the previous picture, that looked not too different than a telescope you might have looked through during a stargazing event at a local university or at a local astronomy club. This radio telescope is designed to detect light that is much redder, much longer wavelength than the light that we see with our eyes. So it looks a little more like a giant satellite dish in how it collects that data. This particular dish is actually 300 feet from end to end. You can see a little building and a little car in front of it for scale. It was one of the most powerful radio telescopes on the planet and made groundbreaking observations from this corner of West Virginia until one evening when the telescope abruptly went from this to this. It suffered a catastrophic failure and collapse and rendered the telescope completely, unsurprisingly, unusable. The telescope ultimately had to be rebuilt. But sitting at Subaru, I was convinced that someone had tried turning this telescope off and on again. So I was now faced with the problem of what to do. Did I give up crucial PhD thesis data when the telescope was probably fine? Did I take the risk and worry about breaking one of the largest pieces of glass in the world? And this is the story that I actually use to open my book, and the story that I usually tell people when they ask me what being a professional astronomer is like, because it gives us this behind the curtain glimpse at how we take the beautiful photographs that we're all used to seeing of space. It's really not hard to sell people on the mysteries of space and the wonders of astronomy. We've all marveled at images like this and sort of wondered at the big questions that astronomers ask. You know, what is out there? How old is the universe? Where did we come from? Are we alone? But we don't often think about how we answer those questions or how we get to these pictures or what astronomers actually do all day or all night. If you ask someone to picture of a professional astronomer, they usually picture this. They usually picture a man. He's got a beard and is wearing a lab coat and is standing next to a little telescope in the middle of the night that he's looking through with his eyes. And it's a very fair picture. Anybody who has stargazed in someone's backyard or during a stargazing night has done exactly this. So you just imagine a professional doing this on a grand scale. And this is certainly the picture that I had of professional astronomy when I was a little kid. This is me at age 6. And I'm proudly sporting a NASA t-shirt showing the Hubble Space Telescope, which had just been launched that year. I knew, even as a tiny kid, that space was exciting, that I wanted to study space, but I had no idea what that meant. We had a little telescope that we would occasionally take out in my backyard. That's me and my dad. And I just imagined that I would be spending a lot more time at a telescope like that. It's an understandable perception because most of us don't know a professional astronomer. there are only about 50,000 professional astronomers in the world. So I did not, for a very long time, get a chance to sit down with an astronomer and find out what the job would actually be like. My first glimpse of that actually came when I was in college, and I went to my first professional observatory. This is Kitt Peak National Observatory in the southwestern United States. And I went there with a research advisor who was about to take me on my first, what we call, observing run. We were going to spend 5 nights pointing one of these telescopes at nearby very cold stars to see if we could understand how they worked. We showed up on the first night and walked into the observatory dormitory and kitchen, where astronomers were sitting down eating dinner, their first meal of the day, before they went up to the telescopes. My advisor sat me down, he introduced me to everyone around me, and said, "This is Emily, she's my student, and this is her first time observing at a telescope." And everyone immediately said hello and got very excited and started giving me advice, saying, "Drink some coffee so you can stay awake, but remember to stop drinking it at about 4 a.m. or you'll be too wired. You'll never go to sleep once the sun comes up and your night ends." Somebody else said, "Oh, watch out for your feet. We have poisonous scorpions around here." And there was actually a woman who had a scorpion crawl up the inside of her pant leg and sting her while she was observing. This is true. Her office is now down the hall from mine here at the University of Washington, Seattle. Someone else said, "Well, I know a guy who was observing and he had a raccoon crawl into his lap and he didn't know what to do. He was stuck in the dark in the middle of an observation. He just sort of pet it until it fell asleep." And someone else said, "Well, I know a guy who was at a telescope when the dome got struck by lightning." And someone else, "I know a guy who was at a telescope when the mirror got shot." And the stories just got more and more ridiculous. And I was sitting frozen at the lunch table with a bite of food sort of stuck halfway to my mouth. I couldn't stop listening and I couldn't decide whether I wanted to stay and hear people tell stories all night or run off to the telescope and start getting stories of my own. And I realized later what all this storytelling was meant to do. It was people sort of welcoming me to the field and sort of showing me this is what this strange, odd little job that only 50,000 of us do can actually be like. These are some of the funny things that can happen to you while you're working at a telescope. It gave me a bit of a glimpse into what my career was going to be like, but even I really could not have predicted all the different places that astronomy would have taken me. I think the thing that most surprised me about astronomy is that in the pursuit of studying space, I wound up really discovering amazing corners of my own planet. I never would have predicted sitting at dinner that evening that almost 20 years later, I would have been in Auckland, New Zealand. I traveled to New Zealand from, those dates are actually wrong, I'm sorry, from March to June of 2023 to work with Dr. Jan Eldridge at the University of Auckland. She leads a team of researchers that is one of the foremost teams in the world at studying binary stars. So two stars orbiting one another. If you've seen Star Wars and have seen the double star sunset on the planet of Tatooine, these are exactly the types of stars that Jan and her team are experts on. I've been curious about binary stars for years, and Fulbright finally gave me a chance to go work with some of the best researchers in the world on this topic. I also got the chance to explore other parts of New Zealand. I got the chance to go down to the South Island and visit the University of Canterbury Mount John Observatory. That's me there with my family, and you can see my baby son and I, baby Leo, standing in front of the MOA telescope at Mount John Observatory. That's a 1.8 meter telescope, so the mirror is a bit smaller, but it's been optimized for a very different type of observing, and I'll talk a little bit about why telescopes like this are so important at the end of my presentation. I never, though, would have imagined as a teenager sitting at Kitt Peak that I would be traveling to and all over New Zealand for my research as an astronomer. And that surprise and that experience is what I tried to capture in my book, The Last Stargazers. I really tried to take readers on this behind the scenes tour through what it's actually like to be a professional astronomer and how much our job is evolving over the years as technology begins to play a bigger and bigger role in how we do scientific research. As part of this book, I wrote about my own experiences, but I also interviewed more than 100 of my colleagues and asked them for what they thought astronomy was like, their favorite and most incredible stories of working at telescopes, the sort of storytelling round robin that I heard when I was sitting at dinner that night. I mostly just let my colleagues talk, and I wanted to hear what their favorite stories were, but I wanted to make the book more than just a collection of goofy stories or anecdotes. So there were a few questions that I asked everyone. The first question that I asked people was what their most memorable sort of second or third or 10th hand story was of working at a telescope. Everyone told me about their own adventures and their own experiences, but I wanted to hear about the stories that had attained almost legend status in the astronomy community, the stories that were now half true because they'd gotten told and retold so many times. I wanted to go back and get to the bottom of these stories so that I could share them in this book. And people loved answering this question. I got a wonderful mix of different answers and different misadventures at telescopes. But a very common refrain was people telling me with glee about when astronomers made mistakes and when we got fooled at a telescope by something that seemed exciting but turned out to be a little surprisingly pedestrian. I think the most common version of this was people saying, there was this telescope in Australia and it discovered something weird. They thought they were talking to aliens and it turned out they found something funny. What was that? And people couldn't quite remember. And the full story of this comes back to the Parkes radio telescope in Australia. So this is another radio telescope like the kind that I showed you earlier. And I'd explained that these telescopes are designed to detect light that is much, much redder than what we see with our eyes. This means that when we talk about it being dark or we talk about a telescope detecting light, we're imagining a very different type of light than what we see around us. If I could snap my fingers right now and turn the eyes of everybody who's watching and listening into radio detecting eyes, you would see a very different world. You might see the sort of buzzing interference of a Wi-Fi network over your head. You would see a very faint glow from, say, a fluorescent light in your room. You see signals bouncing on and off your cell phone sitting next to you. You might see little flashes from the spark plugs in vehicles driving by outside your window. So there's all sorts of funny little interference sources right here on Earth that produce radio light. And in order for one of these telescopes to work properly, we need to know how to ignore all of that noise, all of that extra light from Earth in order to focus on radio light from, say, a black hole in a distant galaxy or radio emission from a strange dying star. So Parkes Observatory is excellent at this. And they were in the middle of observing one night when they suddenly detected this brief flash of radio light. And at the time, they had no idea what it was. You don't expect to typically see radio light that suddenly flashes you and then goes away. You usually see a constant or maybe slowly varying signal from an object that you've pointed at on purpose. This event was sort of logged as a mystery and logged as unusual and then set aside for a while until a young woman named Emily Petroff showed up at Parkes Observatory. She was a PhD student there, and she had decided she wanted to get to the bottom of weird events like this. She said, I'd like to explain where that came from. I think it could be some cool new astronomical phenomenon. And the folks working at Parkes immediately said, oh, no, don't bother. We've actually been detecting these all the time, and we're quite sure they're something boring. And she asked, well, what are they? And they said, well, we don't know, but we're pretty sure that it can't be anything real. It can't be something strange in astronomy. We think it must be sort of some ground interference, but we haven't explained it. They had actually nicknamed these events perytons, which are mythical creatures that look like one thing, but cast the shadow of something else. And Emily decided that she wanted to try and explain what perytons were in the hopes of maybe sifting through ground interference to get at what this strange astronomical signal might actually be. So she started gathering the data. She actually wrote a research paper that ultimately included every employee at Parkes Observatory. So all the scientists, all the support staff, the secretarial staff, the janitorial staff, because the entire staff got in on trying to figure out where these weird events could be coming from. And her first hint came when she looked at the data and realized that the perytons tended to cluster around the lunchtime hour. So space is a very strange place, but space does not care when lunchtime is in Australia. So this was their first hint. This is an aerial view of Parkes Observatory, and the three arrows there are pointing to three administrative buildings that housed offices, places where scientists and staff could work, and all three of those buildings included break rooms with microwaves where someone could, say, heat up leftovers or make popcorn or whatever they might want to eat. And they homed in on these microwaves as a possible explanation for the perytons. And they did this experiment as scientifically as you possibly can. If you read this research paper, they carefully go through how they ran the microwaves on high and low. They ran them for 10 seconds, for 60 seconds. Every time they carefully microwaved one ceramic mug of water Someone went way down the rabbit hole of reading the entire user manual for an old microwave to figure out exactly how this microwave might be producing radio light. They ran these microwaves over and over, and they weren't producing peritons. The telescope wasn't detecting anything. It very smartly was able to not detect microwave light and just instead look for radio light unperturbed. They finally realized that they were doing this experiment like very careful scientists when they instead acted like hungry people who were watching a microwave run down, standing impatiently next to the door and going 3, 2, oh, close enough, and opening the door before the microwave was done. We all know we've done it. When they did that, they produced a periton. They produced this blast of radio light that was picked up by the telescope. Emily and her colleagues went back to the telescope and were able to look through the old data and clear out all these strange detections from microwaves being impatiently opened. And they were able to determine that, yes, these peritons could be explained by microwaves with some exceptions. That very first strange event that they picked up was not a microwave. Now that they knew what to look for, they could tell that this was legitimately a strange burst of radio light coming from deep space. They've since observed heaps more of these, and there is now an entire field of study based around studying what we know as fast radio bursts. We still don't quite know where these come from. We think they might be the death throes of dying, rapidly rotating, enormous stars, but we never would have been able to ask the question in the first place if we hadn't figured out, oh, well, these are coming from microwaves. We can filter out the microwaves before we get to the science. So I had so many colleagues tell me versions of this story, and they loved telling me versions of accidental detections. You can easily think of how something like an optical telescope could accidentally detect a flash of light. I've talked to people who accidentally detected headlights from cars or a match being struck when someone lit a pipe. But this extends even to some of the most exotic types of astronomy that we do. So this is a very different type of observatory than what I've shown you so far. This is the Laser Interferometer Gravitational Wave Observatory here in my home state of Washington. This is an observatory specifically designed to detect what we call gravitational waves. Gravitational waves aren't light. They're not optical light or radio light or any type of light at all. These are actually little ripples in the fabric of space-time that come from things like two enormous black holes colliding with one another. When two black holes collide, the collision is so powerful and so violent that it can actually send little ripples waving out in space-time. They will actually squeeze and stretch space and time itself on a minuscule level. These were predicted by physics. They were actually predicted by Einstein's theories more than 100 years ago, but detecting them proved almost impossible. It sounded almost like a fantasy until relatively recently, thanks to observatories like this. What you're looking at is two enormous vacuum arms, 4 kilometers in length and perfectly straight. They actually change slightly in height over the ground because they're straight, even relative to the curvature of the Earth. In this little central building on screen that you see in the bottom is a laser that will bounce laser light from the center of the building down those two 4-kilometer arms and back. Now, the arms are perfectly the same length. So if this is done properly and there's no source of noise and there's no gravitational wave passing through Earth and squeezing and stretching the space and time that we're sitting in, that laser will bounce down to the end of the two arms. It will bounce back at the exact same time. It will arrive back at the building at the same time, and we'll have proof that, nope, no gravitational waves have been detected. The lasers traveled the exact same distance in the exact same time. Now, if a gravitational wave does go by, I'm going to very much exaggerate the effect here. One of those arms will be squished and one of those arms will be stretched, so they will now be slightly different lengths. If we fire the laser again, what happens then is that the laser travels down and back from the two arms at a slightly different time. They arrive back at the building staggered, and we get a signal telling us, hey, a gravitational wave has passed by. The engineering and precision involved in building something like this is indescribable, but what you wind up doing is detecting everything else along with the actual gravitational waves. You can detect things like footsteps of technicians walking around in the building. You can detect trucks driving by on highways miles and miles away. You can detect earthquakes happening on the other side of the planet. So the biggest challenge of a gravitational waves observatory is actually not detecting anything else. They've gotten astonishingly good at accounting for footsteps and trucks and distant earthquakes, things like rain hitting the ground. But even they occasionally get surprised. At this observatory, they eventually, at some point, noticed that they were getting these strange little extra bursts of signal and were having trouble explaining why. They looked at one of the cooling pipes in the observatory's vacuum chamber. And this cooling pipe was exposed to the outside in the middle of a hot Washington summer. It was working very hard to cool the instrument, and it had accrued ice on the outside. And they noticed these strange little peck marks on the ice. And whenever they noticed these weird little bursts of signal, those peck marks were there. Someone eventually realized that what they were detecting was not the signal of black holes colliding halfway across the universe. They were detecting a thirsty raven that had been pecking at the ice as it flew across the desert because it was a very convenient source of water. They carefully documented the raven. They took pictures, as you can see, of the peck marks. They had a graduate student go out and try to reproduce the experiment by pretending to be a raven and knocking on the coolant with a hammer. And they eventually realized that, yes, this could explain the errant signal that they were getting. So whether we get tricked by thirsty ravens pecking at our pipes or whether we get tricked by hungry astronomers impatiently microwaving their lunch, people loved telling me these stories of accidental detections. I think they liked the combination of the big universe scale questions that we were trying to ask and the very funny little earthbound things that could sometimes trip us up. Another question that I always asked my colleagues was what they thought would surprise people the most about our jobs. I was writing this book about what life is like as a professional astronomer, something that most people probably had never thought that much about. And the overwhelming answer that came back was that we really have some surprising adventures. We are not just sort of standing next to little telescopes waiting for something to happen. We're traveling in some cases all over the planet or even beyond the planet in pursuit of our research. I talked to astronomers who make a career out of chasing solar eclipses, traveling to wherever you might be able to see a solar eclipse, and one happens on Earth about once every 18 months, dragging scientific equipment with them because the solar eclipse might not be anywhere near an observatory. This picture was taken in Svalbard, Norway, in order to get beautiful, detailed observations of our sun. I talked to astronomers who build specialized scientific instruments and send them high up into the atmosphere aboard balloons or even rockets so that they can get away from as much of Earth's atmosphere as possible and get beautiful, clear observations with their custom-built instruments. I talked to astronomers who observed at the South Pole, where we can build telescopes that can take gorgeous observations in the beautiful, cold, crisp winter air during a South Pole winter that obviously comes with the incredible adventure of wintering over at the South Pole. I also learned the story of the man in this picture who seems at first to be breaking my promise that astronomers do not wear lab coats and stand next to little telescopes. But this man has an excuse. This is George Carruthers, and he is the inventor of the ultraviolet camera. I've talked about the optical light that we can see with our eyes, and I've talked about radio light, which is much, much redder and much longer wavelength than what our eyes are able to see. Ultraviolet light is bluer. Its wavelength is a little bit shorter than what our eyes can see. And that makes it very hard to capture in a camera and very hard to take a picture of. George Carruthers solved this engineering problem back in the early 1960s. And he is standing next to the very first telescope that held his patented invention for an ultraviolet camera. That telescope is actually the only telescope that we have ever taken to the surface of the moon. It was flown to the moon on board Apollo 16 and took the very first ultraviolet pictures ever of our own planet, of nearby stars in our galaxy. The direct successor to this telescope eventually became the Hubble Space Telescope, which is still taking some of the best ultraviolet observations in the world. But it all started with this little telescope that we flew to the moon. My favorite picture on this screen, though, and my favorite astronomy adventure that I tell the story of in my book, is this picture on the upper left. So this is a telescope operated by NASA, known as the Stratospheric Observatory for Infrared Astronomy, or SOFIA for short. It is a telescope built into the back of a specially modified Boeing 747 that is designed to fly up into the stratosphere, so higher than commercial airlines fly. While it is up there, it opens that back door that you can see in the rear of the plane to expose an infrared telescope. This telescope observes light just a little bit redder than what our eyes can see. It doesn't extend to the extreme of radio astronomy, but it gives us the opportunity to again observe a different type of light from stars and pinpoint different strange physics about how stars work. It's able to do this by getting above all the clouds and most of the water vapor in our atmosphere, which would normally interfere with infrared light. The light would just bounce off the clouds and never make it to us here on the ground. Sophia operated out of California for most of the year. During northern summer and southern hemisphere winter, it actually flew down and operated out of Christchurch, New Zealand. And during one of its observations from New Zealand, I actually got the opportunity to fly on board Sophia and get some data for strange stars that I was studying. I got the chance to fly all the way down to Christchurch and then get right back on a plane again. Sophia operates out of the United States Antarctic Program's building and headquarters. We actually flew so far south and so far towards the Antarctic Circle that we were able to see the southern lights out the windows of the plane. To this day, it is the coolest thing that I've ever gotten to do for my job. I'm very sorry to say that NASA's Sophia was unfortunately defunded a couple of years ago. And I think all of us were heartbroken, both because it was a wonderful scientific resource and because, oh my gosh, it was about the coolest adventure that you could have as an astronomer, jumping into an experimental aircraft and catching data from the open back door of a plane while the southern lights just sort of shimmer away overhead. It was unbelievable. So the last question that I asked my colleagues was how astronomy they thought had changed since they had begun their work. We've seen huge technological changes in the field of astronomy, even over the course of a few decades. I talked to colleagues who had been working and observing back in the 1950s, 60s, 70s, and they described observing and capturing images like this. This is a picture of a photographic plate, which was used in astronomy before we moved on to digital detectors. This is actually a small sheet of glass that was chemically treated on one side to darken when exposed to light. So you would take this sheet of glass, fit it into a telescope working in the dark, and then open the telescope to expose whatever you might be pointed at. In this case, a faint, beautiful little spiral galaxy. And then you would wait next to the telescope's instrument and next to that camera with the plate loaded inside for hours sometimes until the tiny bits of light from that galaxy had slowly hit the plate and darkened until you had this beautifully preserved little image of that galaxy. It sounds like a primitive way to take observations, but we got some of our most incredible scientific discoveries out of observations of photographic plates. And you can see the beautiful little image of this galaxy. You can tell that it's a spiral. You can spot little knots of lots of stars and maybe even hints of dust and gas in the galaxy's spiral arms. But once we moved to digital detectors, we really did enter a new era of just how clear and precise these pictures could be. This is a photographic plate of this little spiral galaxy. I'll now change to an image of the exact same galaxy using the Subaru telescope that I described at the start of this talk. And you can see how incredible a picture that is. We're able to take digital images with multiple filters and produce this beautiful color image. You can now see the bright blue shine of the stars just leaping out of the galaxy at you. Those reddish and orangish colors are dust in the arms of the galaxy, blocking some of the light that we see. The amount of detail is just tremendous, and the speed with which we're able to take this data is getting faster and faster. Today, we're starting to build even more incredible new telescopes that are able to further extend our capabilities of how fast we can work, what kinds of images we can take, and what we can do with them. As part of my research for my book, I went down to Chile to visit the site of the Vera Rubin Observatory. This is an observatory named for the woman who discovered the existence of dark matter that is almost done now being constructed. This was what it looked like in 2019. And it has this very beautiful, very simple design. It is taking a telescope mirror that's, again, a little more than 8 meters across. As a reminder, that's how big the telescope mirror is going to be. And it is taking images of a huge swath of the southern hemisphere sky over and over again for 10 years. Those repeat images are ultimately going to give us essentially a movie of the night sky. Now, a movie of the night sky doesn't immediately sound like the most exciting thing you've ever imagined. We imagine the sky is mainly staying still. We might see different constellations at different times of year. You might see something like a shooting star flying across the sky, but we don't usually think of the sky as something that is constantly changing. It is, though. If we had a deep, detailed movie of the night sky, we would see something like an exploding star appear in a distant galaxy, just a little pinprick of light that slowly faded away. I mentioned shooting stars. These are little rocky objects that are burning up in our atmosphere as they reach Earth. A telescope like this would be able to detect tiny moving rocks in our solar system, asteroids that might be getting near, maybe even uncomfortably near Earth, because it would spot them as little tiny background objects scooting through the nighttime sky. It would also be able to detect any star that is getting brighter or dimmer and brighter and dimmer as time goes on. These are known as variable stars, and they're one of the types of stars that I specialize in. And a star can brighten and dim for a lot of reasons. It might be pulsating a little bit. It might be shedding some gas from its outer layers. That gas might condense into dust that blocks our view of the star. The star could have a binary companion that's passing in front of it or getting blocked behind it, slightly changing how bright it looks. But sometimes stars can vary for very, very strange reasons. And these are the stars that I'm the most interested in. I really love studying just the weirdest stars in the universe. And some of the weirdest stars that I've ever had the chance to study are these stars known as Thorn-Zhitgov objects. So a Thorn-Zhitgov object is a theoretical type of star. It was predicted by Kip Thorne and Anna Zhitgov back in the 1970s. And it imagines a big, cold red star that has something called a neutron star for a core. Now, I want to explain why that's unusual. A star like our sun, or any other star that you can see with the naked eye in the night sky, is able to live, is able to support itself against the crush of gravity from the star's own gas, thanks to nuclear fusion going on in its core. These stars basically operate tiny nuclear reactors deep inside them that fuse hydrogen into helium or helium into carbon, and that fusion generates just enough energy to maintain this delicate balancing act in the star, fighting the press of gravity with the outward push of fusion. A star like a Thorn-Zhitgov object would be one of the only known examples of a star that doesn't work that way. Its core would be this neutron star that I just described. A neutron star is the dead leftover husk of a very massive star that has died and its core collapsed. In that star, the battle against gravity has eventually been lost. The core collapses into this tiny, dense object that is actually supported by principles of quantum physics rather than by nuclear fusion. What Kip Thorne and Anna Zhitgov imagined is that you could actually bury a neutron star inside what looks outwardly like a normal star and barely even know it was there. The star would just look outwardly like a big, strange, cold star, but with this neutron star sitting inside it. The way they imagine these working actually comes from the formation from two stars in a binary. They would imagine two stars, both much more massive than our sun, slowly going about their lives and orbiting one another. The more massive of those stars will eventually die and undergo that collapse I talked about. You'll get this rebound shock that we see as a supernova, and what's left behind is that little tiny dense neutron star. That neutron star then either collides with or is swallowed by its companion star, and the companion star puffs up and inflates until it looks like this big, red, cold object known as a Thorn-Zhitgov object. Every other time I've ever given this talk, most folks have never heard of Thorn-Zhitgov objects before, and it's a very strange new little name for a star. If anybody watching this talk reads the webcomic XKCD, Thorn-Zhitgov objects were actually featured on the Friday comic, the most recent comic for XKCD. The joke in the comic was that as a means of trying to make one of these objects, we were going to try to get funding to slingshot a neutron star into our own sun. It sounds completely ridiculous, and it is meant as a goofy joke. We would not actually throw a star into our own sun. But one of my research students is actually simulating what would happen if you did exactly this, if you fired a neutron star directly at a companion star. It's not as strange as it sounds. That big supernova explosion is really violent and could send that neutron star rocketing off in a particular direction. And we're simulating what would happen if we actually buried a neutron star deep inside a companion, and if that could be one way to make a strange object like this. I got interested in these stars years ago and was actually able to get very detailed observations of the chemistry of stars that we thought could potentially be Thornjet-Dove objects. Remember that from the outside, they just look like a big cold star. The only way that we know that neutron star is in there is to get very precise, detailed observations of the chemistry of the star's atmosphere. And when you look very closely, you see little telltale chemical signatures of what a Thornjet-Dove object would look like. This was some of the most exciting observing that I ever got to do. I got to go down to another enormous telescope, this time in Chile, take very detailed chemical observations that I am sorry to say do not look very beautiful. I think when people imagine astronomical data, they imagine something like this, just this beautiful Hubble Space Telescope-like picture. My really exciting data looks like this. It looks like these strips of light where we've actually taken light and sorted it out according to its color. We're looking at light going from bluest to reddest, trying to look for anything unusual. In this picture, it barely leaps out at you, but you can see these little bright spots that one of my colleagues recognized as one of the telltale signs of a Thornjet-Dove object. We now think that we might have found the first evidence that these sorts of stars can even exist. It's one of the more exciting projects that I've ever gotten the chance to work on. And it is actually part of what drove me to do my Fulbright research in New Zealand. I showed that binary star system that the Thornjet-Dove object formed from. This is exactly what Dr. Eldridge and her team specialize in simulating. And I spent several months working with her and her team trying to figure out, how rare, how unlikely is a scenario like this. By traveling around New Zealand and getting the chance to visit some of the other observatories too, I actually got a great look at precisely the sorts of telescopes that we would want to use to observe something like a Thornjet-Dove object. Those enormous telescopes that I showed before, the Rubin Observatory, which is now just about ready to begin observing, would be great at detecting stars that might be Thornjet-Dove objects. They might catch some of the little brightening and dimming variations that we would expect from a star like that. But as incredible as this telescope is, it can't take, say, a close-up look at the chemistry of that star. It can also only look at stars that are relatively far away because the mirror is so big. With telescopes like the one that I visited in New Zealand, a smaller telescope that's able to point at bright nearby stars, we can test the chemical composition of all sorts of bright red stars relatively close to Earth to see if we have any Thornjet-Dove objects right in our backyard. So this is the sort of science that I really like getting the chance to learn about and getting the chance to dig into as part of my research. It's also the sort of science that I really wanted to emphasize in my book, because over the course of this talk, I have presented all sorts of different types of telescopes that we can use. I've talked about small telescopes, enormous cutting edge telescopes, telescopes that we put in the back doors of airplanes. I talked about radio telescopes that work at very different wavelengths. I'm very happy to say that that picture on the lower right is the rebuilt radio telescope that I showed collapsed in West Virginia at the beginning of the talk. As part of our research as scientists, we really want to use every new piece of technology and every new advancement available to us, but we also want to always keep in mind that science is being done by humans and is being driven by human curiosity, and that we need every possible tool available to us in order to do this work. It's heartbreaking that the telescope on the lower left no longer exists. And smaller telescopes in the United States are being threatened with losses of funding simply because there's only limited money available to pay for and build and support telescopes. And I would really love to see us continuing to maintain all sorts of observatories like this to make it possible to travel around the world and speak to experts on these strange sorts of stars that we want to understand. Really, the more that we can support astronomy and the more that we can support being able to answer weird questions and explore strange stars, the more we're ultimately going to learn. So on that note, I want to put up the information to my book one more time. Thank you all very much for your invitation to speak today, and I'm happy to answer any questions that you might have.
Thank you so much, Emily. That was super interesting. If anyone in the audience has any questions, you can unmute yourself or pop them in the chat.
it looks like someone is typing a question in the chat, which is perfect.
Yeah.
I have a question.
Okay.
While we wait to see what's coming in the chat, I had a quick question. You touched on where your own research is going in sort of the near future, which is fascinating. I just wondered if you had any thoughts on, with the kind of the rate of technological advancement, what else you're excited about in coming up in the sort of the next sort of 10-year window.
I'm so glad that you asked this, and there's a somewhat related question that just popped up in the chat. So, what am I most excited about technologically? Um, I showed that giant mirror that I was standing underneath, and just the sheer simplicity of physics says that bigger telescopes are always going to be able to sort of stretch the limits of what we're able to see. There are projects underway to build telescopes that are 30 meters across or even bigger, and I'm so excited to see what happens when telescopes like those come online. That Rubin Observatory that I showed pictures of, my university, the University of Washington, is actually a founding partner in that observatory. I've been getting email messages from colleagues saying, the mirror is in, we're testing it, we're going to point it at the sky in a matter of weeks, which is going to be a huge milestone. So I can't wait to see what it finds. Um, Technologically, there's also really interesting tools that we're going to get to use. That Rubin Observatory, I said it's going to create a movie of the night sky. And what it's really going to create is heaps and heaps of pictures that we can just stick together to make a movie. It's going to produce petabytes of data and just an overwhelmingly huge amount of data. So someone in the chat has asked, how do you see AI impacting your work in the future? It's a broad question, but it's a great question. And that's one of the many ways that AI is going to start to have an impact. Something like being able to take big data or machine learning techniques and apply it to these enormous data sets is a great use of AI. I have plenty of colleagues that are already doing this. I have friends and colleagues who are experts on AI, and trying to understand how to use it and how to use it responsibly in research is a huge part of what we do, because the computational power alone is incredible, and being able to use AI to take a many faceted problem and try to identify sort of surprising science in there is really exciting. I think what a lot of us want to do is combine the sort of computational power of AI with the creativity and the innovation of the people doing the research. So it's a really exciting time and a really exciting set of, new observatories that we can combine AI with right now.
Great, thank you, Emily.
Sorry.
Oh, sorry, there's just another question in the chat. Will the Rubin Observatories movie that you just mentioned also give us a sense of the movement of the universe, expansion/contraction, for example?
That's a great question. And hi, Morgan. Morgan was my program manager for Fulbright New Zealand, and made traveling to New Zealand with a 6-month-old as smooth as it could possibly be. But so this is a great question, and Rubin Observatory actually will give us a sense of the expansion of the universe, and how it will is really interesting, because the way that we are able to study the expanding universe comes from being able to measure distances to faraway objects very precisely and then figure out how fast those objects are moving away from us. One of the best ways that we have to do that is by studying supernovae in very far away galaxies. There are types of supernovae that we are actually able to predict the brightness of very, very accurately. We basically watch the explosion of a star get bright and then get dim again. And how fast it goes up and how fast it goes down tells us how much energy the explosion had and how bright it should be. So if it is supposed to be very bright and it looks very dim, we know it's very far away. It sounds like a really simple description, but that truly is what we're doing. Supposed to be bright, looks dim, means it's far away. And we can measure that distance very, very precisely as a result. We can then study that supernova or the galaxy that supernova happened in and see how fast it's moving away from us by effectively looking at the Doppler shift of the light from that galaxy. If you hear someone leaning on a car horn as the car drives past you, you hear the car horn get higher and then get lower as it drives away from you. We see the same thing with light. The light gets lower, the light gets redder as it moves away from us. Rubin is going to detect hundreds of thousands of supernovae like this. And to date, we've studied maybe a few thousand of them. So in a year, Rubin is going to have by orders of magnitude increased the number of supernovae that we can study like this. So we'll get this unprecedentedly beautiful map of how the universe is expanding.
Great, thank you. Does anyone else have any questions? Oh, there's another question from Paul. As a professional astronomer, how much time do you spend on administration, for example, writing grant applications versus observation and data analysis?
This is an excellent and knowledgeable question. Well, I wrote a Fulbright grant a couple of years ago that worked great, but it is something that we spend honestly growing fraction of our time on, in part because there is no shortage of people who are very excited about becoming astronomers and who fare very well in their training to become astronomers. So we wind up with a large number of people competing for a relatively small number of resources. And this can mean writing applications to get grant funding. This can mean writing applications to get given one of those precious nights of observing on a telescope. It can mean finding funding for our research students. Especially as a more senior scientist at this point, I spend a decent amount of my time writing grant applications. We also do most of the evaluation of these applications ourselves. So I not only spend a lot of time writing applications, I spend a lot of time reading them and evaluating them. I'm on a couple different committees right now that is trying to find as effective and fair, but also efficient means as possible of evaluating applications. I do still get to observe. I do still get to do some data analysis. I am currently searching for more examples of these weird Thorn-Jitgov objects. I mentioned I have a student working on modeling them. I'm trying to find more observed examples of them. And I'm happiest when I get to just sit down and work with the data. But I also recognize how important it is to get funding for students to be able to do it and to evaluate other people's proposals so that the field as a whole can keep doing the work that we're all trying to do.
Okay, great. Thank you, Emily. Yeah, I don't think there's any more questions. Looks like Morgan is typing. Well, oh yeah. Great, lots of thanks coming in. Yeah, thank you everyone for joining us today, and I do hope that you can make it to some of our other Good Works webinars. The next one coming up will be on 3rd of December with 2014 Fulbright alumni Elizabeth Chan. She works in Hong Kong as a lawyer, and her talk will be on AI and arbitration. And yeah, we'd love to see some of you there. Keep an eye out on our socials and our website for updates and times on anything Good Works. And thank you so much again, Emily. That was super interesting. And thanks for coming. This webinar will be uploaded on our Fulbright YouTube channel. Okay.
Thanks, Emily.
Thanks, Emily.
Thanks.